Alright folks, here's your last video for Unit 2. This one's going to be called Electrons and the Electromagnetic Spectrum. So some of you might be familiar with the electromagnetic spectrum. It is the spectrum that includes everything from gamma rays, the deadly rays that turn the Hulk into the Hulk, and all the way to microwaves, the things that allow us to kind of cook our oatmeal in the morning, and every little light spectrum in between. So we're going to talk about how electrons apply to that certain spectrum. So the first thing we have to do is define two different types of states. We have to define a ground state versus an excited state. Atoms have the ability to gain energy from the surroundings, just like we gain energy from the heat that comes out of our furnace. What this does to an atom is it causes the electrons in that particular atom to move further away from the nucleus. So if we have a, let's call this, I don't know, well, let's just make it hydrogen, right? If we have a hydrogen atom, and we can put an electron right there, all right, that's what the hydrogen atom would look like. And then if we excite that hydrogen atom, I'm going to have to do that again. So that's what the hydrogen atom would look like. If we excite that hydrogen atom by putting energy into it, maybe in the form of electricity, let's say, that atom, or that electron rather, will jump up. It'll actually move further away from the nucleus. What will eventually happen is that electron doesn't like staying way out there, because remember, all the positive things are in the nucleus. So eventually it will coalesce or relax back down to its original point. And when it does that, lo and behold, it actually emits something. Sometimes it'll actually emit visible light in the colors that we can actually see. And the type of color that we see corresponds to the distance that the electron actually traveled. So in this case, it traveled from there to there. All right, so let's go a little bit deeper into that. Now, in order to figure out exactly what energy level the electron jumped up to, it's very important to understand that these energy levels are quantized. It's a new term, so I'll define it in a second. So when these electrons are excited, the electron will only move to a certain distance from the nucleus. And you might say, well, how can that be? Well, just think of it like rungs on a ladder. When you're walking up a ladder, you go from rung 1 to rung 2 to rung 3 to rung 4. You don't go from rung 1 to rung 2 to rung 2.5, because if you do, you're going to fall and it's going to hurt. So electrons are kind of the same thing. They go from energy level 1 to energy level 2 to energy level 3 to energy level 4. Kind of interesting to note that the further away they get from the nucleus, by the way, the nucleus would be like down here on the bottom of my slide. Okay, there's the nucleus, positively charged. The further they get away from the nucleus, the less the jump is. So the jump from like that first energy level to the second energy level is enormous. That's really, really big. Okay, but then when they go from, let's say, that second energy level to the third energy level, the jump gets a lot more pedestrian. Or the third to the fourth energy level, it's a lot simpler too. But it's that first jump that's always pretty tremendous. Anyway, these jumps are always quantized. So what that means is that this electron, when it starts right there, if we add energy to it, it will not jump up to the next energy level until it has earned enough energy. And then when it does that, it'll jump up right there. There is no in between. It won't go there. Okay? And that's an important point for us to understand where these electrons actually reside. So this whole concept, the fact that the electrons can only jump to certain distances away from the nucleus, is what we mean by quantized. This means that the energy levels are quantized, which I always kind of think of as being consistent. The energy levels are consistent. It's a consistent jump, same distance away from the nucleus every single time. Now, once electrons actually get excited, once they move away from the nucleus, they are looking to relax again. You know, after all, the nucleus itself is positively charged, and electrons are negatively charged. And so at the end of the day, electrons are always going to want to come back to the thing that's positively charged. And this is what we mean by relaxing. So the energy the atom absorbed is eventually going to be released. Now, we should know something about the law of conservation of energy. We can't create or destroy any. So if we give energy to an atom, that atom will eventually release that same amount of energy. Now, how does it release that amount of energy? Well, first of all, the electrons will relax to their original positions. And sometimes the energy that's released by the atom is actually visible. So it's released in the form of visible light. What's kind of cool is that atoms will release energy that we can actually see, and they'll release multiple forms of energy, which means multiple different colors of light. And that's what we use to identify the different types of elements that we have on the periodic table. So we can see some of the colors the elements emit. For instance, we've got lithium and sodium, potassium, rubidium, cesium, mercury, and neon here. So we've got a lot of alkali metals and then mercury and neon on the bottom. And when we excite these atoms, when we put energy onto these atoms, the electrons start to move further away from the nucleus. When they relax, when the electrons come back towards the nucleus, they start to emit light. So if we pick on lithium, for example, we can see that lithium atoms emit a little bit of red light and a little bit of yellow light and a little bit of green light and then greenish blue light and then all the way to the purple section, okay, all the way down. And if you'll notice, for every single one of these elements, there are no two spectrum that are identical, which kind of makes sense because every single one of the elements has a different number of electrons. So they should all have a different dance that the electrons do when the atom actually absorbs energy. So each element has its own colors, and we kind of call that the fingerprint of the element. And this is really cool because let's say you have a sample of unknown junk, and you're like, well, I really want to know what this stuff is. Well, one of the things we can do is excite that particular element, and we're going to do this in class, so you actually have a visual of what's going on. And when we excite this element, sure enough, different colors are emitted, and we can say, there you go. That's potassium. And potassium's really cool. I like to use that one as an example because potassium, if you take all of potassium's little colors that it emits, the blue and the green and the green and the green and the yellow and the orange and the red and the dark burgundy and whatever it is, and you add them up and you mix them together just like you would mix paints together in a paint studio, you actually get the purple color that I'm circling the spectrum with. So potassium, to our visible eye, when that particular element is excited, gives us a purple color. It's a really neat element. And in fact, anytime you see purple fireworks, you got to give a check mark and a thank you to potassium because potassium is typically the element responsible for that color. All right, that's electrons and the electromagnetic spectrum.